The value for the bond at the end of each year is 1.09 times the value at the end of the previous year. So we're now going to complete the table. So for the amount after year 4, we could either take the amount from the previous year, year 3, and multiply that by 1.09 to get the $21,173.73, or we can plug into our calculator the formula 15,000 times 1.09 to the 4th power. Just remember our bed math and that we have to do the exponents before we do our multiplication. So we would put in the 1.09 to the 4th power first and then multiply that value by the 15,000. For year 5, the formula would be 15,000 times 1.09 to the 5th power. So notice our power is matching the year. We get a value of $23,079.37. We can continue doing this through year 6, and year 7, and year 8, and you should be able to see the pattern now, so that we can find the value at the end of any year by doing 15,000 times 1.09 to the power of whichever year that we are looking for. We're now going to plot the data from the simple interest and the compound interest tables. There are two things on this plot that I really want to make sure that you show. The first is that the graph will start at the value of the principal, in this case 15,000, so it's going to be above the x-axis. The second thing is that the compound interest line will be curved and the simple interest line will be straight. If I ask you to sketch a graph of one of these or both, just make sure that these things are covered. The starting point, above the x-axis, and whether the line is curved and whether the line is straight. The graph shows the simple interest bond is growing in a linear pattern and the compound interest bond is growing more quickly or exponentially, a curve which we will be looking at more closely in Unit 8. For this example, we'll write the equation to find the amount A, the simple interest with respect in t, time in years. A equals P, which is our principal, plus the interest earned, which is our PRT. In this case, our principal is 15,000. 15,000 plus 15,000 times 0.09 times t, which can be simplified to A equals 15,000 plus 1,350 times t. This equation is similar to our y equals mx plus b formula that we did in grade 10, with our 15,000 is our y-intercept, and the 1,350 would be our slope. For the second part, write the equation to find the amount with compound interest with respect to t in years. This is the formula that we just discovered 2 slides ago. Our 15,000 times 1.09 to the t power. If we just changed our numbers a little bit, and we considered an investment of $30,000 compounded annually at 5%, write an exponential function which will represent the final amount, $A after t years. So now our principal is $30,000, and because our interest is 5%, we will now multiply that by 1.05 raised to the t power. Another example. Consider an investment of $750 compounded annually at 3.5%. Write an exponential function which will represent the final amount in A dollars after t years. So here we have A equals 750, which is our principal, times 1.035, represents our interest rate, raised to the t power. In general, if A is the final amount, or the value of the bond, P is equal to the principal, which is the initial investment, I as the annual interest rate, and t is the number of years, we will have the general formula of A equals P bracket 1 plus I raised to the t power. But we don't just deal with interest that is compounded per annum. It may be compounded semi-annually, or 2 times a year, quarterly, which is 4 times a year, monthly, 12 times a year, or daily, which is 365 times a year. There's also the option of continuously, but we're not going to look at that until Unit 8. The formula for computing compound interest is A equals P times 1 plus R raised to the n power. But we're just going to look at our R and our N a little bit more carefully here. So A is our final amount, so that's going to be our principal and our interest. The P is our principal, that's the amount that we start with. We're going to look at R now as being the interest per period. So let's say our annual interest is 12%, and we are going to be collecting our interest monthly. We would go the 12% divided by 12. So each time we collect interest, we're only collecting 1%. Similarly, if we had 12% per year and we were collecting it 4 times a year, we would only be collecting 3% 4 times for our 12%. So we go I, which is our interest rate, divided by how many periods that we're paying in. N is going to be the number of interest periods per year. So if we were collecting it twice a year for 5 years, we would go 2 times 5 to get 10. So we'd be collecting interest 10 times. I know this can be a little bit confusing when we're dealing with multiple periods, so let's take a look at a couple examples. If Miles West invests $5,000 in a financial institution at 6% per annum, compounded annually, calculate his interest at the end of 3 years using the compound interest formula. This is straightforward. We're dealing with per annum. There's nothing fancy here. So we have our formula A equals P, 1 plus R raised to the n power. Principal is 5,000. Our interest rate is 6%, or 0.06. And our n is 3. We're dealing with 3 years. So A equals 5,000 times 1.06 raised to the 3rd power. Throw that in our calculator, and we get $5,955.08. Let's look at Miles West again. Except this time it's still 6%, but it's compounded quarterly for the period of 3 years. Calculate his interest rate at his interest at the end of 3 years using the compound interest formula. So again, we have the same formula. The principal is still 5,000, but our rate is being split up into 4 units, 4 sections, because it's being compounded quarterly. So now our interest rate is 0.06 divided by 4, which is 0.015. And he's collecting it 4 times a year for 3 years, so the number of times he collects interest is 12. So now the formula is 5,000 times 1.015 raised to the 12th power. In this case, he's going to make $5,978.09. Notice that's just a little bit more than it was in example 4. After 3 years, the investment is going to be worth what we just got, our $5,978.09. So the actual interest earned, we need to take away our principal. So the interest earned would be $978.09. Just a few last notes. Note that the compound interest formula calculates the final amount an investment is worth. To find the actual interest earned, you subtract the principal from that calculated amount. Also, note that the investment compounded quarterly, 4 times a year, earns an interest of $978.09, while the investment compounded annually earns an interest of $955.08. When the interest is compounded quarterly, it is reinvested into the principal more often. Since the principal grows more frequently, the final investment is worth more. In general, the more often investment is compounded, the greater the amount of the interest that it earns.